Alright, imagine you're living in some random ancient town thousands of years ago. You've just had a really good harvest and now you got some free time on your hands. And you want to figure out, like, what's going on here? What is all this stuff around me? How does it work? Nobody seems to know. It's time to put on your detective hat and get to the bottom of this. A quick disclaimer, this is essentially going to be an extremely idealized history of physics where every path of investigation turns out to be fruitful. It's important to remember that this is fundamentally not how science works. But, the video is long enough as it is, I gotta leave some things out. So the first thing you might notice is that if you want to really understand the world around you, it helps to be specific. Like, you can convey some useful information by saying your neighbor has a lot of cows, but you can convey a lot more information if you've already agreed on a word that means this many cows, a word that means this many cows, and so on, and then you say your neighbor has 5 cows. And the great thing about these words is you can apply them to anything. You can have 5 cows, 5 chickens, 5 kids. You can even represent more abstract quantities. You can make plans for 5 days from now, or you can divide up the day into hours, minutes, and seconds and talk about those. You can say your neighbor's house is 120 steps from yours, but this is a little ambiguous, so maybe you get a nice big stick and declare its length to be 1 meter. And from now on, if you want to be really precise, you can either use the meter stick itself or cut another stick down to the same length and use that. You can also get a nice big rock and declare its mass to be 1 kilogram and then measure things against that using a balance scale. Another thing you realize is that your memory is not perfect, and it'd be nice to have a place to store this information externally. So you come up with some symbols for these words which you've decided to call numbers, and then you can carve information into stone and come back to it when you need it. And now numbers can get pretty big, so it's pretty impractical to have a completely different symbol for each one. And since you can only count to 10 on your fingers, that seems like as good a place to stop as any. So after 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, instead of creating a new symbol for 10, you just start counting the 10s and the 1s separately. So the next symbol is 1, 0, where the 1 means 110 and the 0 means 0 additional 1s. Then comes 1, 1, 1, 2, etc. And after 99, you write 100, where the 1 means 100, the first 0 means 0 additional 10s, and the second 0 means 0 additional 1s. Now you've noticed that it doesn't matter what you're counting. 2 of the same thing and another 3 of the same thing always gives you 5 of that thing. So you might as well save some time and make this new symbol plus and write 2 plus 3 equals 5. And similarly, you can have 3 groups of 4 things each, and it always comes out to 12 things, so you might as well just write 3 times 4 equals 12. And you can also consider the opposite operations as long as you expand your idea of what a number is. Like if you give your neighbor 3 cows and they give you 2 cows, it's like you just gave them 1 cow, so it makes sense to write 3 minus 2 equals 1. If you give your neighbor 2 cows and they give you 3 cows, it's like they gave you 1 cow. But it doesn't really make sense to write 2 minus 3 equals 1 because it's the opposite situation. No problem, we can just call that negative 1. And if you have 4 loaves of bread and you want to split them evenly among 2 people, each person gets 2. So it makes sense to write 4 divided by 2 equals 2. However, if you want to split them evenly among 3 people, they won't each get a whole number. But that's alright, you can just call it 4 divided by 3, and people will know they're getting a bit more than 1. Maybe you're a bit uneasy with negative numbers and fractions at first, but they seem pretty useful and they behave pretty well, as long as you don't try to divide anything by 0. Anyway, back to the physical world. If you want to know exactly where something is, it seems like you need 3 pieces of information. How far forward or backward from you it is, how far left or right from you it is, and how far up or down from you it is. And actually, if you want to communicate with others, it's probably better to have some shared reference point to measure from. Maybe you build a little marker in the town square along with a few perpendicular arrows, and now you can describe any point unambiguously with 3 numbers. The first tells you how many meters it is this way, the second tells you how many meters it is this way, and the third tells you how many meters up it is. And anytime it's in the opposite direction of one of the arrows, the corresponding number will be negative. So you start playing around with this idea and you come up with variables and algebra and the Pythagorean theorem, which lets you calculate distances using these coordinates. But it's also a little unsatisfying because it tells you the difference between these 2 points squared should be 2, but it doesn't really tell you what that distance actually is. So all you can do for now is call it the square root of 2 and approximate it. In fact, eventually you realize that this number is not a fraction, so you have to expand your idea of what a number is again. Anyway, these coordinates are nice, but it's also nice to be able to just point in a direction and say it's 500 meters that way. So in order to translate between these two ideas, you come up with the concept of angles, sine, cosine, tangent, and all that good stuff. And you start thinking, hey, maybe this could help me figure out what the deal is with those stars up there. Like, I don't know what they are, I don't know how far away they are, but light seems to travel in straight lines for the most part, so I can measure their angles relative to these coordinate axes. So you start spending a bunch of time looking up at the night sky. Now, you don't need any precise measurements to notice that, in general, throughout a single night, every single star seems to be rotating in the same direction. And throughout the year, if you look up at the same time of night, almost every single star seems to be rotating in the same direction, which is slightly different than the daily direction. But the key word here is almost. There's a few outliers that have grabbed your attention, and you want to know exactly what's going on with them. Now, if not for these outliers, it would be pretty natural to assume that the sun, moon, and stars, whatever they are all orbiting around you. But this pattern doesn't make any sense from that perspective. These outliers are all generally moving in the same direction as the other stars, but sometimes they slow down and even reverse direction for a short time. What if they're not orbiting around you? What if they're orbiting around the sun? This seems like it could explain your observations without anything actually suddenly changing direction. Now, after a while of making precise measurements and crunching the numbers, you come up with some quantitative rules that seem to govern how these outliers, which you've decided to call planets, move. Number 1. The orbits seem to be elliptical, with the sun at one of the focus points. And number 2. If you draw a line between a planet and the sun, the area of the region it sweeps out over a particular period of time seems to be constant. Number 3. The amount of time it takes a planet to orbit the sun, squared, seems to be proportional to the cube of the semi-major axis of the ellipse. These rules seem to work great for predictions, but they don't really feel like they're explaining what's causing the orbits to happen. They give you the big picture, but what is actually happening at any particular instant? How does the planet know it should follow these laws? Well, this idea brings up a bit of a problem. How do we even talk about instantaneous changes? Alright, if you want to know how fast you can run, you can measure how many meters you can run in a second. And if you're running at a constant speed of 5 meters per second, it seems reasonable to say that your speed at any particular instant is 5 meters per second. Problem is, that's not what happens. It takes time for you to speed up. So if you're still speeding up after 1 second, what is your speed at 1 second? Dividing 0 meters by 0 seconds doesn't help. Well, one approach is to just say that you can't. You can talk about speed over a particular positive length of time, and you can make that length as small as you want, but it can never be 0. And that seems pretty reasonable, but it just makes things really awkward, and it kind of feels like you should be able to. After all, if you keep measuring speed over smaller and smaller time intervals, it does seem like it's converging on a particular value. So why can't we just use that value? You know what, let's do it. And thus calculus is born. You figure out how to mathematically define this idea, you figure out how to do it in reverse by measuring the area underneath a graph, and you figure out how to calculate these things for all the standard functions that you come across. Now you have no problem talking about instantaneous velocity. It's just the derivative of position with respect to time. And you can take the derivative of velocity with respect to time to get your instantaneous acceleration. Alright, let's see if you can use this to figure out what's going on with the planets. First of all, you look at the simplest possible orbit, which is just a perfect circle with the sun in the center. And here the semi-major axis is just the radius, so the orbital period is proportional to r times the square root of r. Now the second law tells you that the speed is constant, and so proportional to 1 over the square root of r. Now for an object going in a circle at constant speed v, the acceleration points toward the center with constant magnitude v squared over r, which in this case is proportional to 1 over r squared. Now that feels more satisfying, knowing that at all times, the sun is exerting some force on this planet that's causing it to accelerate towards the sun at a rate inversely proportional to the square of the distance between them. And if you apply this rule to the more general elliptical case, you find that it matches your rules there as well. Now you've also noticed that the Earth is a big sphere, and that objects on Earth accelerate down at a constant rate due to gravity. In other words, towards the center. It's not too much of a stretch then to assume that this attraction the sun is exerting on the planets is the same thing as gravity, and that the 1 over r squared acceleration just appears constant on human scales because Earth is so big. Based on Earth's radius, the acceleration is smaller than it would be at the same distance from the sun, but Earth is less massive than the sun, so maybe that makes sense. In fact, the simplest explanation would seem to be that every object exerts this gravitational attraction on every other object, depending on its mass, and that we simply don't notice the effect from most of them because they're either too light or too far away to have much of an impact. You still don't really know why this attraction exists, and it's a little strange that it's transmitted over such a long distance, but this seems good enough to turn your attention to other things. For example, you know how objects move due to gravity, but how do objects move due to, moving them? Normally it seems that an object stands still unless it either falls down due to gravity or gets physically pushed by some other object. But when it's in the air or on ice, it seems pretty happy to keep on moving at the same speed. So it's not really moving something that takes effort, it's changing the speed or direction it's moving. Acceleration. And the heavier something is, the more effort it takes to accelerate it. If you define force to be equal to mass times acceleration, then the fact that gravitational acceleration is proportional to the mass of the attracting object divided by the distance squared tells you that the gravitational force is proportional to the mass of both objects divided by the distance squared, and therefore that you are exerting as much gravitational force on the Earth as vice versa, which is a fun thought. In fact, this is a nice definition because whenever any object exerts a force on another, it seems like the latter object exerts an equal and opposite force on the former. Like if you're standing on a frictionless frozen lake and a big block with the same mass as you comes sliding towards you, and you hold out your arms to spread out the impact over a period of time, it turns out that you'll be decelerating the object precisely as much as it is accelerating you, until you reach the same speed. And if the mass of the block is twice yours, then you'll be decelerating it half as much as it is accelerating you. But either way, the end result will be that the integral of the force applied to you, which is your mass times change in velocity, will be equal to the integral of the force applied to the block, which is its mass times change in velocity. This means that if you add up the mass times velocities of you plus the block, it's a conserved quantity. It doesn't change. That probably means it'll be useful to talk about it, so let's call it momentum. In general, you find that the total momentum of a system is conserved unless acted upon by an outside force. If you repeat the experiment on regular ground, you and the block will both come screeching to a halt, but you will have transferred your momentum to the Earth in an immeasurable but calculatable way by air resistance and friction. Okay, but instead of bracing for impact, what happens if you just let it hit you? Or better yet, keep your bones intact and substitute another rigid block. The results are pretty interesting. For one thing, if the blocks have equal mass, the first one stops in its tracks and the second one starts moving with the original velocity of the first. But in general, when m1 does not equal m2, you find the following results. The first block's final velocity is m1 minus m2 over m1 plus m2 times the initial velocity, and the second block's final velocity is 2m1 over m1 plus m2 times the initial velocity. And the total momentum comes out to m1 v1, the same as the initial momentum, just as expected. But this collision feels more energetic somehow. It's like pure bounciness. Maybe you're not sure how to quantify that energy just yet, but it feels like it takes twice as much of your energy to lift something 2 meters as it does to lift the same thing 1 meter. After all, you're just lifting it 1 meter twice. But if you send the object down a frictionless ramp onto the ice from 2 meters, it's not going twice as fast as in the 1 meter case. You've seen this ratio before. It's that darn irrational square root of 2 again. That suggests that maybe energy should be proportional to velocity squared. And if you calculate the mass times velocity squared for this bouncy collision, you find that it is conserved. Now this velocity energy isn't conserved for that other non-bouncy collision, but you can rationalize that by saying that maybe the energy went into the deformation of your bending arms. Even friction, which slows stuff down, also heats stuff up. So maybe temperature is a form of energy as well. And all these different physical processes are just converting one form of energy into another. Well, even if so, the two easiest kinds to work with are the energy of a moving object, which you call kinetic energy, and the stored energy gained from working against gravity, which you call potential energy because it has the potential to generate kinetic energy, I guess. It's a bit of a confusing name since it sounds like it's just the possibility of energy, but it is energy, just a different type of it. Okay, so you've assumed that, at least near the surface of the Earth, the gravitational potential energy is proportional to the mass times the gravitational acceleration on Earth times the vertical distance traveled, and the kinetic energy is proportional to the mass times the velocity squared. But if you define the kinetic energy to be exactly mv squared, then the potential energy comes out as 2 mgh. And if you define the potential energy to be mgh, then the kinetic energy comes out to be 1/2 mv squared. As far as I can tell, it's arbitrary which one you choose as long as you're consistent. It's like using pi versus tau as your circle constant. You just pick whichever one makes your life easier, which turns out to be the 1/2 mv squared one. Now you still don't really understand what physical stuff is, but you have a pretty good understanding of how it moves. So you shift your attention to other things, like light. What's going on with light? I mean, it usually moves in straight lines, and if that's all there was to it, you might call it a day there. But not always. If you go in the water, hold your hand up at arm's length right below the surface, and move your eyes down to right above the surface, it's clear that there's some sort of weird bendiness going on. By the way, I highly recommend doing this in real life next time you go swimming. It's very entertaining. To further investigate this phenomenon, maybe you could use water or ice, but what you really want is glass. I'm not sure how you get glass. Maybe you noticed little transparent things on the beach after a thunderstorm and thought, hey, this is exactly what I need. It'd be pretty neat if I could make these myself. I'm gonna go make some sand as hot as possible. I don't know. Somehow or other you make some glass and you do some experiments. Since light travels in straight lines in air, it seems like a reasonable assumption that it would also travel in straight lines in the glass, and that whatever weird stuff is happening is just happening at the border. If you take a glass rectangular prism, put it on top of a ruler, and look from precise locations, you can make a plot of the angle the light that reaches your eye is traveling inside versus outside the glass. You see that the light that goes straight up, perpendicular to the air glass boundary, continues straight, and that the greater the angle with the perpendicular line, the more it seems to bend. Past a certain point, it seems that none of the light that comes from certain angles is making it out. But it's not obvious what the relationship between these angles is. Well, what can you do with angles? Trig functions, I guess. What happens if you instead plot the sines of these angles? Alright, that looks pretty conclusive. So when light travels from glass into air, the sine of the angle with the line perpendicular to the boundary gets multiplied by around 1.5. And if you do the experiment in reverse, holding the glass up to your eye, you find that it's the exact opposite. The sine of the angle gets divided by the same value. You can also do it with water and see that the sine gets multiplied or divided by around 1.33. This seems to be a pretty good description, but why the sine? And why these particular numbers? This is all very mysterious. But then one day you're out on the beach and you see a cool rock in the water, so you head over to investigate. Instinctively you realize that going in a straight line is not the fastest way there, because you can move on land a lot faster than you can move in the water. So instead you head near the closest point to the rock on the shore, maybe not all the way there, since the last few meters add a lot to your land distance without reducing your water distance very much. Afterwards you think, that was kind of interesting. I wonder if I can figure out the fastest path mathematically. And you can, and it gives you the exact same angle relation. That's certainly very suggestive. But surely light can't be doing the same thing, right? I mean, you can accept that maybe light doesn't travel instantly, and that maybe it travels at different speeds in different mediums, but this is the planetary problem all over again. How would light know it should take the fastest path somewhere? What could possibly be happening instantaneously to produce this effect? When you're out on the beach again looking at the water, you notice waves slowing down and bending a bit as they reach the shallows. That looks familiar. What if light is a wave? You imagine the light reflecting off some particular point on the ruler as a three-dimensional sine wave, propagating outwards in a sphere. But for ease of visualization, you consider a two-dimensional circular slice of it. You don't know what it is that's waving, but you can model it by assigning a number to each point in space. And just as each column of water pulls its surrounding columns of water up and down, increasing and decreasing the height of the water to create a wave pattern, maybe each point of this mystery light field exerts influence on its surrounding points, increasing and decreasing this number in the same way. Well, if this is the case, what does it even mean for the light to take a particular path, if it's just a spherical wave expanding outwards? You suppose if you were to block a particular path and that stopped the wave from reaching the endpoint, that would count. But can't the wave just go around the blockade? How does this work? Say you have a wave originating at some point A, and you're trying to observe it at some point B. Now the wave can reach B in all sorts of ways, but if you were to construct a narrow channel so that this one path is the only one it can take, then the phase of the wave at B, meaning like where it is in its cycle, will simply be equal for the time it took for the wave to propagate through that channel. But if you had a different channel that took a different amount of time for the wave to propagate through, then the phase of the wave at B would be different. And if you opened up both channels, then each wave would exert its force on B independently, and the value of this field at B would be the sum of the values of these two out-of-phase waves. If the phases were exactly opposite, they would cancel each other out and produce no disturbance. In general, we'd have to sum up the individual waves contributed by all possible paths from A to B. Now consider what would happen if the wavelength was really, really small. On this scale, any noticeable difference in path time essentially randomizes the phase contributed by that particular path, leading to destructive interference. The only paths whose waves constructively interfere with each other are those that are really, really close in path time. In the limit of zero wavelength, the only path that matters is one where if you make an infinitesimal change to it, the time taken for a wave to propagate along that path does not change. If you block everything near that path, the waves from the other paths will all interfere with each other and give you pretty much nothing at B. This condition is satisfied for the fastest path. After all, if you make an infinitesimal change and the time decreases, it's not a minimum, and if the time increases, then you can make the opposite change to get it to decrease. So if the wavelength of light is really small, this behavior actually makes some amount of sense, and you don't need to prescribe light any knowledge of the future to explain it. You still don't know where these constants are coming from, but then there's a lot you still don't know about physical properties of materials. And you also still don't understand what's waving to produce light, but that's okay. You'll save that for another time.